Hello and welcome to my GTC 2021 talk titled Simulate the World and Everything in It. My name is Paul Richmond from the University of Sheffield in the United Kingdom. I'd like to thank my colleagues Rob Chisholm, Peter Hayward, Matt Leach and John Charlton who contributed towards some of the content within this talk. The motivation for this talk is the simulation of complex systems. And complex systems exist all around us, whether it be flocks of birds or the movement of people, all the way down to kind of much smaller biological scales like the behaviour of cells or even the brain itself. So complex systems really typified by this idea of emergent properties. So the fact that individuals interact together and as a result there is some global emergent property that we can observe. Now there's lots of difficulties in simulating complex systems, particularly with GPUs. So GPUs can and have been used to accelerate agent-based simulations, but doing so for a very general case is very, very difficult. So it's really this trade-off between having simulation that can cover lots of different cases, the general case as we'll refer to it, versus very specialized code that is an implementation of a particular model. Now, supporting a general case or having an agent-based simulator, an agent-based modeling is a way in which you can describe a complex system and then simulate it. Having a general case agent-based simulator is advantageous because it separates the model description from the implementation. So separating implementation from model description is highly advantageous because it vastly simplifies the verification and testing of the model and the simulation code. So there's been lots of talk obviously about this in the UK in particular, where there's been questions raised about the trust of epidemiology modelling. It's great to see that there's articles which have confirmed that the modelling that has been used was reproducible, but reproducible code doesn't necessarily mean that it's good and well engineered code. And in fact, kind of having this separation between the model and the simulator means that it's much easier to understand a model and to infer whether or not the model is kind of correctly described. So this talk then will address some of the fundamental challenges around agent-based modeling simulation on GPUs. Agent-based modeling on GPUs is not entirely new, and this work is building very much upon previous work that I've described at GTC in the past. So in particular talking about Flame GPU. Flame GPU1 was something which allowed a general case of agent-based model description to be targeted to GPUs and achieve nice simulation results. This is an example of the Olympic Village simulating over 60,000 people in real time. Similarly, I've talked in the past about transportation modelling and smart city simulation. So this is both pedestrians and vehicle simulations and looking at the performance advantages of doing so. Really what I'd like to address in this talk though are the emerging challenges for agent-based modelling on GPUs. So where are the current limitations in what has been described previously? Really, I've tried to summarize those as 4 points. So one of those is big GPUs, the fact that GPUs have increased in parallelism. The second is maintenance and architecture of simulation code. The third is flexibility and integration, so being able to describe models in a very flexible way, integrate them with other third-party tools and other third-party code. And the fourth is stochasticity, so the fact that a complex system with it being emergent is quite often stochastic as well. So you cannot simply run a single agent-based model and expect that to be representative of behaviour. You need to run multiple simulations and observe characteristics which are representative of the simulations that you have run. The first challenge then for agent-based modelling on GPUs is big GPUs. And by big GPUs I mean GPUs have got increasingly parallel. So when I first started writing code for general agent-based modeling on GPUs was back in around 2010. GPUs have increased by almost 14 times the level of parallelism that they support in the number of CUDA cores. So it means that there's 14 times more potential for simulating larger population sizes. The big challenge, of course, with this is that as you add complexity to a model, it generally means that you have less homogeneous agents. So it means that you have agents performing perhaps slightly different behaviours at different times. This means that you have smaller populations of things that can perform the same behaviour, which ultimately leads to divergence and poor utilisation on the GPU device. So as the level of parallelism has increased, this has potentially got worse, because what would previously be a small population of homogeneous agents is now no longer enough to keep a GPU device busy. So we need to do creative things to keep the GPU working efficiently. So one of the underlying principles of developing an agent-based model for the GPU using the Flame GPU approach is this formal model of agent interactions. So the idea behind this then is to abstract the underlying implementation. Modelers write models rather than writing parallel programs, and instead describe an agent-based system as a form of state machine. So there's a lovely complex definition of what an X machine is, but effectively it's a state machine with communication via messages. So for a very simple model, and this could be something like a flock of birds or a schooling type model, then we can describe it using kind of this really simple diagram. So we have circles represent states, and the square boxes represent functions or behaviours. The green diagonal box represents a piece of information that's exchanged via messages. So each agent can effectively send its location and potentially its velocity in the first function. By the time we get to the second function, read locations, we are guaranteed that agents transitioning into a new state, there's some form of global synchronization, which means that we can guarantee that all of those location messages exist. Agents can then read those locations and then move into the final state, which will involve updating their position and ultimately moving. So this formal description of an agent is really nice because it's inherently parallel. The fact that we have these states means that we have the opportunity for synchronization and can build much more complex models that can be parallelized. So this then is an example of that very, very simple model. This is called the circles benchmark model. Within this model, agents simply communicate their position and they try to then move by considering a repellent and an attractive force. So they form these kind of beautiful spherical formations as a result of a stable state in which they're balancing kind of the repellent force, meaning that they keep a distance from their neighbours, with an attractive force that means that they form effectively groups. What we can see is that eventually these spheres will kind of, if there's some velocity of the group, they will slowly kind of merge as well. And that's a relatively simple example, but of course a real complex agent-based model may be more like this. So it may contain huge numbers of states and behaviours and individuals and different types of communication. And you can see just from this diagram, which represents the model of the European economy, that mixing the implementation along with this model description would very, very quickly lead to something that was very difficult to maintain. Whereas Flame GPU allows us to have a really nice clean separation of these two things. So in order to utilize big GPUs effectively, one of the things that was vital for the next generation of simulator, which we've called Flame GPU 2, is to make sure that we can exploit parallelism within the model. So this wasn't very easy to do with the previous Flame GPU 1 design, but within Flame GPU 2, we've added this concept of concurrency. So concurrency exists where we have two different agents performing performing a different function. Because they don't depend on each other, there's no dependency between these two agents. They can independently perform these send location functions, and this means that those functions can effectively take place at the same time. So we can launch multiple kernels at once, make use of the multiple streaming multiprocessors on a GPU, and effectively keep the GPU busier, even with potentially smaller populations. And if we build a dependency analysis graph, which we can do by considering the agents and their interactions via messages, we can build a complex graph like the one on the previous slide and develop layers in which it's possible to have this concurrency. So in order to benchmark and understand this, we've implemented a species version of the Boyd's model. And the Boyd's model is essentially just a simple flocking model. So there's not, within this benchmark, there's non-interacting between species. So species are individual and respond only to their own species. But we can procedurally kind of increase the number of species to understand what the impact is on performance. So speed up in these two graphs is measured as a result, or is measured compared to the non-concurrent execution within the new version of Flame, within Flame GPU. So it's within Flame GPU 2, sorry. It's broadly representative of the performance of Flame GPU 1 and what had been achieved previously. And the results are from a single V100 using CUDA 11. So what we can see in this is that brute force communication, so this is where every agent is interacting with every other agent, is much better at demonstrating performance improvements through this concurrent approach. So the reason for that then is that the kernels are simply longer running for brute force communication than in the spatial case. In the spatial case, the kernels are actually run quite quickly, sorry. So we have aspects of serialization around kernel launching, which effectively limit speed up for very large numbers of species within spatial communication. So there's still work to do on this. There are areas where we can improve concurrency further and reduce aspects of serialization, but to start with, it's a good start. We're able to get at least some concurrency and demonstrate some performance improvements for large complex models. Of course, what we do see is the number of species is increased massively, that we do see some performance degradation. So once the device is over subscribed, we're effectively adding serial work in the scheduling of the kernels and creation of the waves and tails of threads being launched. So it does eventually kind of tail off. This example, along with any of the other examples that are used in this talk, is available online. It's open source. All of the results are reproducible, and you can download the example and reproduce the results yourself if you would like. So the second area of significant challenge for general agent-based modeling on GPUs is maintenance and architecture, and reproducibility really is critical when it comes to research software. So I'm involved in running a research software engineering team at the University of Sheffield, as well as being president of the Society of Research Software Engineering in the UK, who works very closely with the Software Sustainability Institute. So research software really does have a kind of a credibility issue in terms of a lack of training for researchers to develop good software and employ good software engineering practice. So it's really important, particularly around a kind of complex system simulation, that simulators have kind of built using good practice, so that they have appropriate testing, so that they're being developed by experts who understand GPU computing, so that they can be performant, but most of all so that they are kind of implemented correctly, and there's a high level of confidence that they will produce the right result. One of the main challenges then with Flame GPU 1 was the way in which models were specified and generated. So in previous versions of Flame GPU, you describe your model using an XML syntax, and template files would then parse that XML by using XSLT templates, which would then generate simulation code which could be compiled along with any specific descriptions of behaviour and generate a final executable. And this was a very powerful approach and very, very useful for generating very performant code. The difficulty with this is a number of things really. So the difficulty is around kind of testing template files. Adding new features is not the same as just writing new code, because it needs encoding into templates that can then be expanded, which means testing of the thing that is produced and created from the templates becomes very, very difficult. So what's really needed is a new approach that's able to be much more expandable and flexible and develop good and utilize good software engineering practice. So Flame GPU2 then is API driven rather than template driven. So this is advantageous as it reduces the amount of duplicate code that would otherwise be generated through templating, but it means that there's quite a bit more complexity required to making a library that supports the generalized case. I'm going to go through some examples in a moment that show a very basic utilization of Flame GPU2 so that you can understand how that works. But effectively there's now a single library file that encodes all of the different behaviors and communication types, and users write a model by describing how that model, what that model looks like in terms of the agents and the behaviors. And you can do that with procedural script. Because we're able to do this now procedurally, it's possible that we can have a Python version of this, and I'll talk a little bit more about that in a moment. So the overall API can be kind of classified in this kind of simplified version of the hierarchy. There's a bit more complexity to it than this, but the code is documented and the API is documented. To start with, what you have is a description of a model then, and that's as simple as defining a model description object. The second thing that you would describe is then the messages. So this is the communication between agents. So Flame GPU1 had a limited kind of subset of communication types, and Flame GPU2, with it being API based, means that we can expand upon those considerably. So we have classic communication types like brute force messaging, spatial messaging, so within an interaction radius. So we also introduce array messaging, so this is somewhat like a discrete messaging, like a chessboard type of approach that agents may interact over, as well as bucket messaging, which is very effective for building things like networks. So next you would describe an agent, and an agent is described using an agent description. You can add different variables to agents. So these are effectively state variables that can be manipulated by agent functions. So this would be things like position. You do that simply within the API by using a templated function to specify the type and naming the variable using a string. Next, you can add agent functions or agent function descriptions by saying agent.newFunction, and that accepts a function pointer to an agent function, which follows the kind of the prototype described on the slide. Environment variables can be defined using an environment description, so these are useful for things like properties which are accessible to all agents. They may change in between iterations, in between simulation steps, but they're consistent within or read only within a single simulation step. The last thing to do is to add a layer, so a description of layers, which determines the kind of the dependence between functions. So we're also adding functionality at this point to allow you to define your functionality in terms of a dependency graph. So rather than explicitly listing layers, instead what you can do is describe dependencies between agent functions, whether they be messages or on other functions, and that will then automatically build the dependency graph and layered concurrency for you. In order to run a simulation, you need to be able to take the existing model description, which consists of agents, environments, messages, and initialize it using a CUDA agent model. Once you have a CUDA agent model, you can create a population of agents. Now you could possibly read this from an XML description, or you can procedurally generate that description, so you can procedurally generate that population by iterating over it and setting particular variables. The variables that you set are the variables that we described or would be available to the agent in the previous slide. We can then set that population within the the CUDA model and set the number of simulation steps that we would like and perform a simulation. So there are other aspects that you could add in, like step functions and logging functions, but we're not going to go into all of those within these slides. One thing that is important is the description of agent functions themselves. So these determine the actual behaviour. These represent the square boxes in that dependency graph that we saw previously. So something like send messages or receive messages. So this first example then describes the output message function. So it has two parameters, an input message type and an output message type. Because this function doesn't describe the parsing of any messages, it doesn't have an input, then message type is message none. And we can see the way in which we interact with the API on the device is that we use this flame GPU singleton object to specify the message out and set a particular variable. So this message out variable is defined as having an ID and an X and a Y. And we can query the properties of agents by saying flame GPU get variable. The last thing that you notice here then is that we return a value which represents whether or not the agent persists within the simulation after the execution of this agent function. The second agent function I've got is slightly more exciting, as this describes message iteration. So in this case we're describing the move function. So in fact this move function is also doing the input of messages. We can see that it has an input type of message brute force. We can see within this that there's some use of getting agent variables such as ID, X, Y, and Z from agent memory. We're also getting some environment variables such as a repulsion factor and a radius, and we are iterating over then the input messages to get the positions of neighbours. So because this is brute force messaging, it's assumed that we will iterate over all of those messages, perform a distance calculation at some stage and update the X and Y forces. The forces would then be used to update the agent's X, Y, and Z position. So as you can see, the specification of agent functions is doing something clever behind the scenes, because we're naming agent variables using strings. So this is necessary because we cannot build individual structs that represent agents like we did in Flame GPU 1. To do so would require templated generation of those structures, and that's something that we'd like to avoid. As such, we need like a fast method for returning a memory location from a named variable. So where we say get variable X, we need that to effectively point to the memory location of a particular agent instance. So a particular thread needs to go to a particular memory location to return that value. And there's a number of different ways of doing that. So the first is through compile time string hashing, and the second is through just-in-time compilation. And what we've done with Flame GPU 2 is implement both of those things. Compile time string hashing then works as you would expect. It uses the compiler to transform a string into a hash or into a numerical value. So it does this by using template metaprogramming. We can define a number of templates, and a simplified version of that is described in the example on this slide, where we can effectively translate the string by stripping away individual characters and appending a hashed character to the remainder of the string. And this means that we can perform the entire hash at compile time, and then we only then have to deal with hash collisions in terms of translating that hash value into a lookup effectively into memory. So there's various different things that we can do in terms of error checking and size checking to make sure that the variable that's requested by a user, say they request variable X of type float, to make sure that it is in fact a variable that exists and that the variable is of the same type. Now those checks obviously add latency into the process, so we've defined an optional compile time macro called seatbelts, so you can run effectively without seatbelts, which will omit some of those checks, but it's only really safe to do that if you've pre-run your program to make sure that your types are correct. Just to summarize what happens with compile time hashing, then we can look at this diagram. So initially we start with something within one of our agent functions, which corresponds to device code, where we say get an agent variable, in this case a variable called x. Well, that's compile time hashed into an integer value. The hash lookup can then be applied as a device function, which will look up the pointer to a piece of memory, and those pointers are stored within a hash table in device constant memory. So because all agents will query the same variable at the same point, that read from constant memory is done as a broadcast, so it's reasonably efficient. Of course, it adds a small amount of latency, but it's generally quite efficient. The hash table itself is populated at runtime depending on the agent description and the agent vector or the population data that's set. So option 2 or option B is just-in-time compilation. So the way that we do this is by implementing another version of curve called curve runtime compilation. So this is simply a drop-in header which, instead of doing hashing and lookups, instead has got like a large switch type statement dependent on the variables that exist for a particular agent function and particular agents that are going to be looked up. Same for messages and environment variables. And effectively what happens is that we again use compile time string evaluation to do a very, very fast lookup. The compiler, because we designed this function using again template metaprogramming, reduces the lookup of a variable effectively to a single lookup, which is very, very quick. In theory, we could directly embed the pointer or the location in memory of a particular agent variable within the code, which would make it extremely fast. However, as that pointer is likely to change throughout the lifetime of a simulation, instead we use constant memory again to store a pointer to that piece of memory, which can then be configured at runtime. So as with the previous example, we have a very similar situation that we have a function, an agent function that says get variable. Again, it's called x and it's of type int. So we do just-in-time compiled string switch or string evaluation, and that will return to us the pointer to a particular variable. In this case, oh sorry, it would be this one, address of variable x. Again, this is pre-configured, this lookup table as part of the runtime code on the host side. In order to understand the performance, then, we've implemented the circles benchmark model. So this was the model earlier in the talk where we saw that kind of almost flocking-like behaviour. The circles model is one which is used throughout kind of Flame publications and Flame documentation as a relatively simple benchmark. It consists of 4 agent variables and 3 agent functions. So the benchmark model effectively then has been scaled by changing the environment volume. So we keep the density of agents exactly the same density as you observed in that earlier video, but we change the size of the environment, and ultimately that increases the agent count. So both of these graphs show exactly the same data, it's just one of them is zoomed in. Obviously brute force communication we're seeing takes considerably longer than spatial. We see that the impact of using runtime compilation is quite significant, order almost a 2x performance improvement over the non-RTC build. And then for the circles model in spatial, we see that there's still a performance improvement for RTC, but it's not quite as significant. That is just simply down to the latency that is introduced by having a hash lookup function, which is obviously repeated many times within the brute force case. So this code again is available to download and rerun and reproduce these results. So one of the questions you may ask with Flame GPU is how big can we go? So there's almost 2 answers to that question. So the first is how many agents can we simulate in parallel, and that's a very different answer to how big a model can we design. The amount of agents that you can simulate in parallel and keep the device fully utilized varies depending on the agent function that you write. It's generally in the order of kind of hundreds of thousands of agents, although heavy register usage may reduce this. In terms of the number of agents that we can support on a single device, well, on a 32 gigabyte V100 GPU, we can support around about 200 million agents that will fit in memory at once. And that's deduced from the memory scaling experiment that we've run by actually measuring memory utilization, which is reported in the graph on this slide. On an 80 gigabyte A100, we estimate we could simulate 500 million agents of the circles model, and that would obviously be adding multiple waves and tails of agents to keep the device busy. So the third challenge for general agent-based modeling on GPUs is really this idea of flexibility and integration. So C++ is a fantastic language and a fantastic performant language as well, but increasingly modelers are wanting to use higher level languages, things like Python, and using template generated code that we had previously. It's very difficult to map and have Python interfaces. So fortunately, our just-in-time compilation means that we can effectively design agent functions at runtime and compile them at runtime, and that means that we can write bindings for the Python language, which is something that we've done using Swig, which is it's really nice because it then means that we can integrate that with other third-party pieces of code like scikit-learn, and use things like GAs to do parameter optimization and model discovery. So the fourth challenge of agent-based modeling on the GPUs that I'd like to talk about today is stochasticity. So this is it's really important because if we run a simulation multiple times with different seeds, we can observe very different emergent properties. And here's an example of a pedestrian model where with slightly different random seeds used for the initial speeds of agents, we see that agents will behave in very different ways. So we have this situation where everything kind of gets stuck on the left-hand side, and similarly everything kind of passes neatly by on the right-hand side. And this can have a significant impact on the emergent properties. In this case, it would be the total kind of journey duration time that we observe. So what we've in fact done within Flame GPU2 is introduce the idea of ensembles of models. So no longer do you just define a single simulation. Of course, you can run a single simulation if you like, but you can also define an ensemble of models. And an ensemble may be exactly the same model, but with a different parameter seed multiple times, or it could be the same model with different initial parameters. So that could affect the distribution of the initial agents, or it could affect the global properties or the environment variables. So like with the circles model, we saw the attractive and repulsive force. Just the same, you could vary, say, the maximum speed of agents or pedestrians moving around in a busy environment. So this is something that we have adopted for the purposes of COVID modelling. So we have a project where we're working with RSSB and now supported by the UKRI, which is aiming to understand the boarding and alighting of passengers at the train platform interface under social distancing conditions. So typically these models are quite small, nowhere near big enough to keep a GPU busy, but we typically need many thousands of simulations in order to parameter tune these to observe emergent properties that are representative of the real world conditions that we can measure. In order to benchmark the impact of ensemble models in Flame GPU2, what we've done is create a benchmark which consists of the Boyd's model running on ensemble mode, so using slightly different random seed in each case. And what these graphs show is that we have, so they show an increasing ensemble size for both brute force and for spatial modeling. So this is brute force message communication and spatial messaging between the agents. What we see then is that the average simulation time tends to reduce to some stable state. So the reason that it reduces is because we're increasing the throughput within the device. so that the latency of completing a single model is reasonably high, but as we add more models, we're able to reduce that average kind of simulation time by having higher throughput. So we see that that is the case kind of across both brute force and spatial models. We see that that impact is obviously far larger for small population sizes. So the graphs on the top show reasonably small population sizes, and that's what you would expect to be able to get better device utilization on small population sizes, as large populations are more likely to occupy the device for small numbers of ensembles. So what's next for Flame GPU2 then? Well, we're currently working on a range of models as well as finalizing the code for release. We're currently applying Flame GPU2 to the simulation of neuroblastoma within the EU project Promage. So this aims to simulate whole tumour scale simulations. So this is somewhere between 10 million and 1 billion cells per centimetre cubed. We need to simulate tumours of roughly 25 centimetre cube volumes. So the approach of doing this is to use a multi-scale approach. So we're not going to simulate the entire tumour at the agent-based level. We're going to use patches of simulations tied to a mechanical model which calculates stresses of mechanical stresses within the tumour itself that are then fed back in at the cellular level. So this uses another feature of Flame GPU2, which is the idea of submodels. So we can use hierarchical modeling to resolve contact forces. So we describe a submodel that is iterative and will resolve forces to a particular acceptable level, and then that submodel runs as part of a larger model which encodes the actual cellular behaviour or the biological behaviour. So another model that we're developing and applying Flame GPU2 to is the immune system simulator for TB vaccination. So this is a project called Strichivad, another EU project. So this model is hugely complicated. It's 13 agent types, 170 functions, roughly 60 different message types, and 200 plus environment variables. So we can see in this slide just how complicated that Strichivad model is. So the names of functions have been removed from this due to kind of NDAs that we've had to sign around this model, but you get an idea about the complexity of the model and certainly how having a simulation framework that can deal with scheduling of agent functions and dealing with concurrency within the model is absolutely vital to having an efficient implementation. So in order to conclude my talk, I'd like to kind of conclude with the statement that GPUs can be applied to accelerate agent-based simulations, but doing so for a general case is actually very difficult. What I've done within this talk is tell you about how Flame GPU2 builds upon almost a decade of experience in agent-based modeling simulation on GPUs in order to address some of the key kind of complexities or issues that are a challenge for mapping agent-based models onto GPUs. So in particular, I've talked about the flexibility without losing performance. So this is the idea of having an efficient simulator which can be applied in a wide variety of domains and at different scales. I've talked about how to expose high levels of parallelism, both for small ensembles or for complex models with lots of concurrency. We're able to utilize effectively the extra and increasing levels of parallelism within the GPU effectively to get good performance from an agent-based model. I've also talked about the flexible interfaces with respect to Python's bindings. So Flame GPU can be used both within C++ and Python. And I've talked about support for very large simulations and high throughput parameter exploration through the use of ensembles. So what I would say is go and try Flame GPU2 now. Hopefully by the time you listen to this talk, it's very, very close to being in alpha or beta release. If you are a person who does agent-based modeling and you want to simulate large complex systems beyond those that you're capable of doing on a CPU, then please do get in touch with me to discuss that. Thank you very much. So I'm going to move on and answer some questions about Flame GPU2, which have come from NVIDIA and from common questions that we quite often get asked about the software. So the first of those then is, how does Flame GPU2 compare with the same running on a CPU? And what are the challenges when comparing performance between GPU and CPU? Well, this is a really difficult question to answer in terms of making those comparisons. And really the challenges are comparing the same things. So it's very difficult to know what to compare Flame GPU to. So it is, as far as I'm aware, the only general purpose agent-based simulator on the GPU. We can compare it with, say, the original Flame for the CPU, in which case we see outrageously high performance speed-ups for the GPU, as original Flame was single-threaded, but with MPI distribution in mind for HPC clusters. But the two can do very different things. So Flame GPU is very good for reasonably simple agents, very large population sizes, whereas Flame is perhaps slightly better suited to very small populations of very, very large memory-intensive agents. So really there is a challenge in comparing with the CPU. The other thing that you could do is compare with other CPU simulators, so other agent-based modeling simulators, in which case Flame GPU2 compares very, very favourably. There's various references of papers that we've published that show that. Or the other thing to do is compare Flame GPU2 with implementations of specific models. So in one of my previous GTC talks, I talked about smart city simulation, and in particular we looked at comparing a Flame, and this was Flame GPU1 rather than Flame GPU2, but a Flame GPU model of transportation compared with a kind of a purpose-built transportation simulator that was optimized for multi-core. We saw kind of 30-40x times speed up. So it depends, how does it compare to the CPU? It depends massively on what you're comparing it against. If you're comparing it against a general purpose simulator, then Flame GPU likely does very, very well. One of the challenges, of course, is people who are typically using CPUs for agent-based models are used to simulating things at reasonably small scale with maybe a few hundred agents, because that's the computational limit of the tools that they're using to do it in reasonable time. Flame GPU completely smashes that boundary by giving the opportunity to simulate kind of tens and hundreds of millions of agents. So it needs fundamentally new models to fully exploit and fully utilize it to its best potential. So the second question is the simulator able to leverage multiple GPUs at the same time? If yes, how would it scale? So through the use of ensembles, it's absolutely possible to use multiple GPUs at the same time. So that effectively will schedule different simulations within the ensemble onto different GPU devices. So that doesn't work with MPI or anything like that at the moment, so they have to be effectively on the same or accessible from the same kind of host. But it would suit very well something like a DGX1 or some of the V100 boxes that we have within our high performance computing system. So it's able to leverage those. The speed up that we see if your ensemble is big enough is linear up to the size of the number of GPUs, and then once they become fully saturated, we see it kind of being sequential increase in time, as you would expect. What we haven't done is we haven't implemented support for models that are larger than a single GPU. So if you have a model that has, well, on an A100, for example, we could go up to 500 million agents. If you wanted to do 600 million agents, then we wouldn't be able to support that on currently as it is, mainly because we've not come across models that require that level of scale. If that's something that you do need, then please do talk to us, as it's something that we could implement, but at this stage have not found a specific need to do that. So the third question then is Flame GPU able to run simulations on the CPU where there's insufficient parallelism for the GPU? So this is really interesting, because there are certain parts of a model, even a very large and complex model with very, very many agents, where you may end up with certain agents in particular states where those populations end up being very, very small. and no number of concurrent executions or ensembles is enough to keep the device kind of fully utilized. Ensembles obviously do help with that, and so does concurrency, but there is potential for certain parts to be executed on the CPU. It's something that we've considered in the design of the Flame GPU2 software to be able to have concurrent CPU execution for very, very small populations. And implementing it is actually not too difficult. What's difficult is getting the balance right between those two things. So deciding at runtime where things should be scheduled, and there's a lot of active research going on around how to do that. So it's something that's on the development pipeline, but probably not a high priority at this stage. So I'd just like to end by saying thank you for listening to my talk. Please download Flame GPU software and give it a try. And if you'd like to get in touch with me about simulation of complex systems, then please reach out to me at the email address provided. I look forward to answering your questions on the online platform. Thank you.